wrong because it leads to mate attraction or territory defense, right? That's adaptive. Evolutionarily, you could say, well, the ancestor species sang. Developmental, the birds had to be taught, right, to sing by their parents. And something that immediately causes the behavior could be something like day life. So when the days get longer, it's springtime, it's time to sing, or weather changes. Another one here would be vocal cords, or a brain system, something that's immediately causing the behavior, a mechanism. Okay. So we watched one media submission together with the lemurs. Thank you for whoever sent me that. But another one that I got, which was pretty cool, was an Instagram post about different eyes. And this is actually really relevant because we're talking about sensory systems. So of course, different animals have different shaped pupils. And this was a really informative post talking about different animals and why they have differently shaped pupils. And the cool thing here that I'd like you guys to do on your own time to kind of, prepare yourself for your tests and such, is to kind of look through these examples. And they give you examples, right? So here we're looking at cuttlefish pupils, and they give you an explanation for why their pupils are shaped a certain way. But you can look through those examples and think, which of Tinbergen's 4 questions are they answering? Because when you look through the different posts, so this is a cuttlefish, but we also have horses and snakes. They give different reasons for why the pupils are shaped that way. So I think that's actually really cool. So these are fun to look through and think to yourself, which questions which of Tinbergen's 4 questions are these answers answering? So I won't go through them all, but it's pretty neat to read about. Okay. So first we're going to start out with how the textbook starts out talking about sensory systems, and they talk about this famous paper, What is it like to be a bat? And it's a philosophical paper that was intended to counter a reductionist viewpoint about consciousness. But now it's been used quite often to describe the experience of animals, the subjective experience of animals, and how it's kind of inaccessible to us as humans, right? And there's this quote here, I'm restricted to the resources of my own mind. Okay, does anyone have any idea what that means in this context? Any thoughts? Yeah.
Like, you can think or even understand or comprehend what, like, another species or another organ thinking about because we have never thought that way or had any thinking that way.
Right. I don't have W-shaped pupils, for example. Right? We are restricted to the resources of our own minds. Pretty good quote. So let's watch a little bit of a video about this. Found this video pretty good, talking about an animal's Umwelt. So that's an important term that we'll talk about in a bit.
Has its own sensory world, its own thin slice of the fullness of reality that it can detect. Evolution has shaped the senses of animals according to their needs, but no animal can sense everything. No animal is perfect at everything. There is so much information out there that to be able to detect it all would be an overwhelming experience and also unnecessary. There's also a cost to the senses. Senses don't come for free. To build a sense organ and to maintain all the neurons that feed into that sense organ takes up a lot of energy, which is why their senses are so refined and so constrained by their evolutionary needs. So the word Umwelt was popularized and defined by a German zoologist named Jakob von Uexküll in the early 20th century. It comes from the German word for environment, but he meant the animal's sensory environment, and that's the specific set of sights, smells, textures, and sounds that animal has access to, and that another animal might not. When you really think about the senses, you do start to understand the very different kinds of information that those senses offer their owners. So we obviously taste with our tongues, but a catfish is essentially a swimming tongue. It has taste buds all over its skin. If you put little pieces of food near the flank of a catfish, it will be able to taste it and turn around and stand up. For most animals, taste is about food. It's about trying to work out whether something is worth eating or not. And for humans, food is something that we put in our mouths. But if you're a very small animal, food can be something you land on. And which is why for many insects, taste buds are some things that are found in their feet as well as in their mouths. A fly landing on the apple that you're trying to eat can taste it just by walking on it before you put it in your mouth. I, like most of you, have two eyes. They sit in the front of my face and they point forwards, which means that my visual world is always in front of me and I walk into it. But most birds have eyes on the sides of their heads, which means their visual world is around them. They often have close to wraparound vision, seeing to the sides and also a little bit to the back. And that kind of wraparound vision is really hard to wrap your head around. And then, of course, there are changes that can occur over an animal's lifetime. So the umvelt of an adult might be different to the umvelt of a juvenile. Jumping spiders are very driven by vision. They have excellent eyes, but those eyes also become more sensitive as they get older, and more sensitive to light, which means that I think the world of a jumping spider will get brighter as it ages. One scientist described this to me as a jumping spider watching the sun rise as it gets old. So a sea otter has very sensitive paws. They don't look very sensitive, they look like these weird sort of cauliflowery mittens. They have a sense of touch that is equal to our exquisitely sensitive fingertips. One of the key differences is that they are also extremely skilled at using that sense of touch. They're very fast about making touch-based decisions. A sea otter will dive down into the ocean and very quickly root around with its paws. It will grab that sea urchin, yoink that clam, and then rise to the surface before eating its food. A sea otter doesn't have the benefit of blubber that a whale or a walrus might have. It has very thick fur, but it can find enough food to eat because it has not only very sensitive hands, but very fast hands too. Even in a completely dark room, where the very large eyes of an owl might not be of much use, they can still hear, and they hear really well. The dish of feathers around an owl's face that gives it that distinctive owly look acts as a radar, funneling sound towards its ears. Those ears are incredibly sensitive, but they also have a unique trick that allows the owl to work out exactly where sound is coming from. Based on when sound arrives in my ears, whether it first arrives at the left or the right, I can tell where a sound is coming from in the horizontal plane. I can't do that trick in the vertical very well because my ears are level with each other, so sound arises both of them from above and below at the same time. An owl solves this problem because its ears are offset, so they're asymmetrical. So one ear is slightly higher than the other, and when sound arrives at that ear first, the owl knows where in the vertical plane its target is, and that's why an owl in the dark can land exactly on a mouse. It's why owls in the wild can bust through snow to pick up scurry rodents that you couldn't even see. One of the primary uses of scent in the animal kingdom is for navigation, for finding your way around a landscape. You know, my dog Tycho absolutely can do this. He knows where we are by cross-referencing his memories of the smells of the neighborhood against what he's smelling at any given moment. But there are other animals that use scent for navigation in even more extraordinary ways. A lot of seabirds, the group known as the tube nosers, use the odourscapes of the ocean to find food. The ocean looks featureless to us, right? We can glide over it and just see this endless expanse of uniform blue. But it's not featureless to an albatross. Underwater features like mountains and valleys leads to concentrations of nutrients, which then concentrate food, plankton, and then krill, the kinds of things that a seabird might eat. And so the ocean has this undulating odorscape, odors that reveal the concentration of possible food, and then areas of no scent that reveal scarcity in the deep. Elephants can do this too. Elephants can navigate long distances. Obviously, they have a trunk. They are constantly scanning about with this extremely elongated nose. You know, they'll react to the imminent arrival of rain. People have suggested that they can find buried sources of water by smelling it. It's quite difficult to understand exactly how elephants smell because they are large, intelligent animals that are difficult to work with. Part of this relies on us using our imagination. It's like watching their incredible behavior, looking at their trunk, and trying to just make educated guesses about what their olfactory world might be like. There's a wonderful quote by Marcel Proust that I think captures what's magical about the involved concept. He said that the only true voyage would be not to visit strange lands, but to possess other eyes, to see the hundreds of universes that each of them sees. That's how I think about the sensory worlds of other animals. I think that when I get to empathize with the smell world of a dog or the touch world of a sea otter, I feel like I'm traveling, like I'm leaving the confines of my own body and my own lived experience and going on this fantastical voyage into the world of another creature.
So that's a really good summary of kind of this idea of an umwelt, and a few examples too of different sensory abilities of different animals. Right, so an umwelt is the perceptual world in which an organism lives. And this contrasts with another term, the umgebung, which is the perception of the organism's world from the human perspective. So animals have specific sensory adaptations to their environments. We can look at the different eyes of different animals, and this was discussed a little bit in the video. But if we compare the eye of a deep sea fish, an owl, and a human, we see some differences there. And the same thing when we look at an owl and a horse, right? So, like they said in the video, humans only see in front of them, right? But a horse, and a lot of prey animals as well, can see all the way around them. And this makes sense, right? If you're a prey animal, you need to be able to see predators coming. Owls have two different fields, and a lot of birds have different fields of vision as well. So they have monocular and binocular vision, just like we do. But it's slightly different because they have different adaptations. They have different needs from their environment. They've evolved differently, right? They have a different evolutionary past. They have to solve different evolutionary problems. All right, this is the day of videos. Another video about eyes, and this is a very similar kind of theme to what we've been talking about so far, but it's great to have a lot of examples to kind of drive this point home. Okay.
what most people think of when they look at the world, they think other animals probably see the world pretty much the same way. And only with time we realize that of course other animals don't see the same things we see. That takes us to a sort of philosophical question is, what is the animal actually seeing? It's impossible to know because it goes into a brain that's very alien to ours. It goes through the processes that we don't use when we process visual stimuli. The animal does things with that information that we don't do, so it's really hard to know. The most simple eyes just tell an animal when it's light and when it's dark. And then you've got eyes like ours that have color vision and very, very good spatial vision and can see very complex detail.
The development of eyes can be categorized into 4 stages, from simple to complex. Stage 1 is the simplest form. Light falling on just a few photoreceptors allows an animal to sense light and dark. At stage 2, organisms can now tell which direction light is coming from. In stage 3, 2 distinct eyes appear. The first is a cupped eye with more photoreceptors. The second is a compound eye that adds more cups. Both types in stage 3 can produce crude images of objects. In stage 4, the most advanced eyes perform complex visual tasks. Lenses, corneas, and irises focus light on photoreceptors, creating sharp, clear vision. This entire evolution, from simple to complex, could theoretically happen in less than 500,000 years.
People have asked me if I could be any animal at all, what animal would I like to be in terms of their vision? It would only be right to say this since I work on that so much of my time. I would really like to know how manuscripts see the world. Their perception of the world is so different, both in terms of their sense of color, their sense of parts of the spectrum that we don't see at all, and also the way that their eyes are multiple, so each eye sees the same thing multiple times from different points of view. I think I'd probably, if I got myself into the mind of manuscript, I'd have no idea what was going on, and I would never be able to tell myself, oh, this is how they see it. That's the thing I'm afraid of. But I'd still like to spend at least a few minutes seeing how manuscript sees the world.
Perhaps you're asking then, why not have all the sensory systems? Well, sensory systems are pretty costly, right? A good example of this is that cavefish, there are different species of cavefish, and when a certain species is living near the surface, they have eyes, but no eyes living at a depth where there is little, light. So here are those 2 different morphs of cavefish. So on the top, of course, they have eyes, you can see them there, but on the bottom, that's a species with no eyes. So sensory systems are costly. If you're living in the dark all the time, you probably don't need photoreceptors or eyes, right? So another important concept is known as the sensory drive hypothesis. And it's basically species separated into different environments may develop sensory adaptations to their environments that then result in speciation. So basically, what we're saying here is think about those cavefish, right? They're in different environments, they have the same evolutionary history, but now one's in the depths, or not in the depths, just in caves with no light. And the other one's near the surface with light. Maybe eventually that results in a type of speciation, right? Because they need to develop sensory adaptations for those different environments. But of course, those sensory system changes must be heritable for evolution to act on them, right? And a cool example of this work is explained in your textbook, but basically they had guppies in this kind of arena. So you see those like striped bars, those are moving. And guppies have this behavior where when they see the movement, they'll swim with it. So this is nice because you can change the color of those bars and see how sensitive their color vision is. And you can breed different guppies for those changes. So some guppies are more sensitive. This is before speciation happens to certain colors. And you can take those guppies that are good at seeing that and breed them. And what you find is that guppies bred for color vision do show those generational differences. So this is some evidence of the sensory drive hypothesis. Another important term is sensory bias. Okay, so sometimes animals can respond with increasing vigor to exaggerated versions of naturally occurring stimuli. So what does that mean? This is a nice example of sensory bias in these fish. So basically these fish here, they have this sensory bias for this long tail. So eventually what happens is that point there gets longer and longer. There's a sensory bias for this kind of shape. Right, so these are, and they're called, they're sword fish. Or platyfish. So swordfish, as in the sword at the back, not like a swordfish. So platyfish females prefer males with long tails, even though platyfish do not have long tails. So right, there's the swordfish and the platyfish. The platyfish don't necessarily have those long tails, but you can add them on, and they still have this sensory bias. So what you're seeing, indeed, is the tails that they've added to the backs of the fish. So that's a sensory bias for this long tail. So basically what you see is these sword tail males have exploited this sensory bias for sexual selection. Okay, another concept, the supernormal stimulus, is an exaggerated response to exaggerated stimuli. So here we have this bird being exposed to different kinds of sizes of eggs. So basically, in general, there might be some natural variation in the size of eggs, right, when they lay their eggs. And these birds will try to pick the eggs that are the largest to take care of, because those will be, you know, the chicks that will be stronger, better off, right? Perhaps that's the thought. But you can even expose these birds to a gigantic egg that they would never actually lay, and they'll still spend all of their time incubating this egg. So that's what's known as a supernormal stimulus. So it's an exaggerated response to exaggerated stimuli. You wouldn't actually see this size egg in nature, but they still spend most of their time incubating this size of egg.